Take a moment now to lie down. Let your body relax and close your eyes. Feel the quiet around you, the weight of your limbs sinking gently into the surface beneath you, and allow your mind to rest. Tonight, we will drift together through the vast stretches of space, exploring a mystery that has puzzled scientists for decades, a force invisible, yet shaping the universe in ways we are only beginning to understand. Don't miss a night of fresh documentaries. Hit subscribe and share your location in the comments. What's the time in your corner of the world? All right, one more quick question before we begin. As you settle in, let the thought arise. What is pushing the universe apart? In the early 20th century, scientists looked at the sky and began to measure the distances and movements of galaxies. One of the most remarkable discoveries came from Edwin Hubble, who studied the light from distant galaxies and noticed something strange. The light, when analyzed, showed a shift toward the red end of the spectrum. This redshift, as it was called, indicated that these galaxies were moving away from us. Every galaxy, without exception, seemed to be receding. It was as if the universe itself was stretching, and every point in space was slowly moving farther from every other point. This observation led to the first understanding that the universe is not static, it is expanding. The distances between galaxies grow with time, a fact that was both exciting and unsettling to the minds of scientists. Hubble's work gave rise to what we now call Hubble's law. This law states that the farther away a galaxy is, the faster it appears to move away from us. The rate of expansion is measured by a number known as the Hubble constant. While the value of this constant has been refined over the years, the principle remains clear. The universe is not standing still. Space itself is stretching. This stretching is not like galaxies moving through empty space. Rather, space itself is increasing between objects. Galaxies are carried along like leaves floating on a gently widening river. The more distant the leaf, the faster it drifts from where we sit. The implications of an expanding universe are profound. If the universe is growing now, then in the past it must have been smaller. This simple idea leads to the concept of a beginning, a moment when all space, matter, and energy were contained in a much denser state. While scientists would later explore this beginning in detail, it was the evidence of expansion itself that provided the first clue. By measuring the speed and distance of galaxies, it became possible to trace back in time and estimate how long the universe had been expanding. Simple mathematics, combined with careful observation, suggested a finite age for the universe. This age would eventually be refined to roughly 13.5 billion years, a vast number almost beyond comprehension, yet measurable through the light that travels across the cosmos. Redshift observations also revealed a surprising uniformity. Galaxies in all directions were moving away from us, not in any single direction. This isotropic expansion suggested that the universe has no center and no edge, at least not in the way we usually imagine such things. Every point in space experiences the same stretching, so from anywhere in the universe, an observer would see the same phenomenon. Galaxies drifting away, space expanding. This concept challenged human intuition, which tends to imagine a central point from which things spread. In reality, expansion is uniform, happening throughout the fabric of space itself, carrying galaxies along like passengers on an invisible cosmic conveyor. Scientists then turned to precise measurements of light from distant objects. They examined not only the shift in light, but also the brightness of certain types of stars known as standard candles. Among these, Type Ia supernovae would later become particularly important, but even in these early days, astronomers were attentive to patterns in light that could reveal distances and motions. Careful spectroscopic studies confirmed that the redshift was not a local phenomenon. Galaxies millions of light-years away showed the same tendency to recede. The evidence for expansion became undeniable. The expanding universe led to a deeper understanding of how matter behaves on the largest scales. Gravity, familiar on Earth and in the solar system, influences the motion of planets, stars, and galaxies. Yet, at cosmic distances, the interplay between gravity and expansion becomes more subtle. Gravity pulls matter together, tending to slow any motion, while the stretching of space moves objects apart. Initially, scientists expected gravity to dominate over vast scales. The universe, they believed, might be slowing down, its expansion decelerating over time. But the early measurements only gave a partial picture. Observing distant galaxies is challenging, and the precise rate of change of expansion remained uncertain. The idea that the universe might slow or stop its expansion also introduced the concept of critical density. If the amount of matter in the universe reached a specific density, the pull of gravity could halt the expansion eventually, possibly leading to a contraction. If density were lower, expansion would continue indefinitely, gradually slowing but never ceasing. These scenarios were theoretical predictions based on known physics. They offered a framework for understanding the ultimate fate of the cosmos, long before dark energy became a factor in the equation. Every model depended on careful measurements of galaxy speeds and the total matter present across cosmic distances. Observations were limited and uncertainties remained. Measuring the light from galaxies millions or billions of light-years away involves accounting for cosmic dust, motion within galaxy clusters, and other subtle effects. Yet even with these challenges, astronomers gained confidence in the general trend. The universe is expanding. Every measurement reinforced the picture first revealed by Hubble. Redshifts increase with distance, space stretches, and all of it is part of a grand, coherent flow. It is a silent, relentless motion, imperceptible in our daily lives, yet measurable across the night sky. As the decades passed, the expanding universe became a foundation for modern cosmology. Scientists developed models to describe how galaxies, stars, and gas clouds evolve within this growing space. They realized that the very distribution of matter and energy must influence the expansion itself. Small fluctuations in density, amplified over billions of years, give rise to clusters and superclusters of galaxies. The cosmic web of matter is shaped not only by gravity, but also by the overall expansion rate. Studying this web provides clues about both visible and invisible components of the universe. The discovery of expansion also reframed the way humans think about time and distance. Light travels at a finite speed, so observing a distant galaxy is equivalent to looking back in time. A galaxy 1 billion light-years away shows itself as it was 1 billion years ago. The expanding space stretches the wavelengths of light, encoding both motion and distance in a single measurement. Every observation becomes a window into the history of the universe, a record of how expansion has shaped its evolution over cosmic time. Even within this simple, observable framework, questions lingered. Why does space expand at all? Is there a limit to expansion? How does the expansion interact with matter, energy, and the laws of physics? These questions, subtle but profound, hinted at something beyond ordinary matter and energy. Scientists began to suspect that the universe's expansion might be influenced by a hidden component, something that does not emit light or interact strongly with atoms. This silent, invisible factor would one day be called dark energy, though at the time it remained purely theoretical. The seeds of this mystery were planted in every measurement of distant galaxies, every spectral line that revealed a redshift, and every calculation of cosmic distance. Understanding the expanding universe requires more than observing movement. It requires thinking about the nature of space itself. Space is not a passive container. It has properties, and its growth stretches distances between objects. Unlike motion through space, expansion is motion of space. Galaxies do not push through a medium. The medium itself enlarges, carrying everything within it. This subtle distinction is key to comprehending the universe on large scales. It reframes questions about motion, energy, and force. In this context, even the vacuum of space, empty as it seems, can have effects, influences, and roles in the cosmic story. From these observations, scientists derived a first rough picture of the universe as a vast, growing network of galaxies, moving apart in all directions, stretching across a space-time that itself is dynamic. This understanding laid the groundwork for future discoveries, including the acceleration of expansion and the realization that visible matter accounts for only a small fraction of the total energy budget. The expanding universe, once a simple observation of redshifted light, had become the foundation for one of the greatest scientific mysteries. It is a story written in the sky, measured in wavelengths of light, and unfolding across billions of years, quietly and inexorably, beyond the reach of human touch, but within the reach of human thought. As the universe stretches outward, the invisible hand of gravity continues to play its role. On Earth, gravity pulls objects toward the ground, keeps the moon in orbit around our planet, and holds the planets around the sun. These familiar effects are immediate and easy to observe. Yet gravity also operates across the vast distances of space, between stars, galaxies, and clusters of galaxies. It is a force that attracts, that pulls matter together, shaping the structures we see. In the context of an expanding universe, gravity acts as a counterforce, attempting to slow the growth of space itself. Scientists realized that on cosmic scales, the delicate balance between expansion and attraction could determine the fate of everything. Before the discovery that the universe was accelerating, physicists expected gravity to dominate over time. They imagined a universe born in expansion, gradually slowing as the pull of matter worked against the initial outward motion. If enough matter existed, gravity might eventually halt expansion and even reverse it, leading to a contraction or collapse. Alternatively, if the universe contained too little matter, expansion would continue indefinitely, but at a decreasing rate. These possibilities created a framework for thinking about the long-term destiny of the cosmos. Gravity, though weak across large distances, accumulates over billions of light years, guiding the future of all galaxies and clusters. Calculating the influence of gravity on cosmic scales required careful thinking. Newton's laws describe the force between two masses, but the universe contains billions of galaxies, each with countless stars. To predict the behavior of the universe, scientists needed to consider the total mass of matter and how it is spread throughout space. The idea of critical density arose from this approach. Critical density is the precise amount of matter that would allow gravity to just balance the expansion. If the actual density exceeds this value, the universe would eventually stop expanding and collapse. If it is lower, expansion would never cease. Critical density became a central concept, a benchmark for understanding cosmic destiny. Yet measuring the total mass of the universe is far from simple. Visible stars and galaxies account for only a fraction of the total matter. Much of the universe is dark, composed of material that does not emit light, known today as dark matter. Estimating the density of the universe requires observing the motion of galaxies, the behavior of galaxy clusters, and the bending of light caused by gravity, called gravitational lensing. Each measurement provides a piece of the puzzle, gradually revealing the amount of mass that exerts a pull across space. The challenge is enormous. Distances are vast, timescales are long, and signals are faint. Yet through patient observation, scientists have developed models that capture the large-scale influence of gravity. Gravity's effect on expansion is subtle and cumulative. On small scales, such as within galaxies, gravity dominates completely. Stars orbit galactic centers, clusters hold together, and cosmic structures remain bound. But as distances increase, the pull of gravity weakens, spread thin over enormous volumes. The stretching of space itself becomes significant. Galaxies separated by billions of light years experience both the residual pull of mass and the ongoing expansion. Predicting the resulting motion requires combining our understanding of gravity with precise measurements of cosmic distances and velocities. Small errors in distance estimation can lead to large uncertainties in predictions, so observational accuracy is critical. By considering the interplay of expansion and gravity, scientists constructed models of the universe's history. If matter were dense enough, expansion would slow, halt, and reverse. A lower density meant continued expansion, gradually slowing but never stopping. These models described three classical possibilities: a closed universe that eventually collapses, an open universe that expands forever, or a flat universe that slows to a near stop. Each scenario depends on the amount of matter and energy present. Calculations involve both the laws of motion derived from Newton and the general principles of relativity, which account for the curvature of space caused by mass. Together, these ideas allowed predictions of the universe's past and future behavior. Observationally, testing these models required looking at distant objects and measuring their movement. Galaxies act as markers, moving with the flow of expanding space. By comparing their velocities at different distances, astronomers can infer how expansion has changed over time. This requires careful calibration of light signals, understanding the intrinsic brightness of stars, and separating local motion from cosmic expansion. The process is painstaking. Signals from distant galaxies are dim, sometimes distorted by intervening material. The farther we look, the older the light we receive, giving a glimpse into the universe's history, but also introducing potential errors in measurement. The interplay between expansion and gravity also revealed the importance of unseen mass. Observations showed that galaxies move faster than expected, based on visible matter alone. Clusters of galaxies exhibited gravitational effects that could not be explained by stars and gas alone. This led to the postulation of dark matter, a form of matter that interacts gravitationally but is otherwise invisible. Dark matter contributes to the overall density, influencing the slowing effect of gravity on expansion. Its presence is crucial for understanding the cosmic tug-of-war between attraction and stretching, yet it is only one part of the story. The other, more mysterious component would emerge later as dark energy. Despite these uncertainties, early measurements suggested that the universe might be close to flat, with matter density near but slightly below the critical value. This indicated a universe that would expand forever, but slowly, gradually approaching a halt over vast timescales. Such predictions relied on assumptions about the behavior of gravity, the amount of mass, and the structure of space itself. Each measurement refined the picture, though observational challenges remained. Cosmic distances are immense. Signals take millions or billions of years to arrive, and even the most careful observations leave room for interpretation. The universe, in its expanse, hides many secrets behind faint light and enormous emptiness. Gravity is not only a slowing force, but also a shaper of cosmic structure. Its pull gathers matter into stars, galaxies, and clusters, creating the cosmic web that spans the universe. Filaments of galaxies connect across hundreds of millions of light-years, while vast voids remain nearly empty. This large-scale structure is influenced by both gravity and expansion. Gravity pulls material together, while expansion stretches the space between structures. The balance of these effects determines how galaxies form, move, and cluster. Understanding this balance provides insight into the invisible forces at work, including the mysterious component that later would be called dark energy. The theoretical exploration of gravity and cosmic fate also prompted consideration of the early universe. Shortly after the Big Bang, matter was dense and tightly packed, so gravity dominated completely. Expansion was rapid, but gravity worked to slow it. Over time, as space stretched and matter thinned, the slowing effect became less pronounced. Models predict that if only ordinary matter existed, expansion would gradually decelerate toward a halt. The observed acceleration in the late 20th century, however, revealed that something else was counteracting gravity, something that pushes outward rather than pulling inward. Until that discovery, scientists believed the universe's fate was largely determined by matter density alone. Measuring the slowing of expansion is complicated by the nature of observation. Light from distant galaxies must travel across billions of light-years, passing through regions with varying density, gravity, and motion. Astronomers must account for local gravitational effects, the movement of our own galaxy, and the intrinsic brightness of celestial markers. Even small uncertainties can lead to significant differences in inferred expansion rates. The painstaking work of collecting and interpreting data has spanned decades, requiring ever more precise instruments and methods. The cosmic tug-of-war between gravity and expansion unfolds subtly across time, observable only through careful study and analysis. By the late 20th century, the universe's expansion and the role of gravity had been measured with growing accuracy. Observations suggested a universe that is vast, dynamic, and expanding, with gravity exerting a measurable but incomplete influence. These studies set the stage for the later discovery of accelerated expansion, revealing that the cosmic tug-of-war is more complex than previously imagined. Gravity shapes the structures we see and influences motion, but it does not tell the full story. Hidden forces, invisible yet powerful, play a crucial role. Understanding gravity at cosmic scales provided the foundation for recognizing the surprising behavior of the universe, the acceleration that would point to dark energy, and the need to rethink the ultimate fate of everything around us. Gravity, then, is both familiar and mysterious. It acts in ways we can see and ways we can only infer. Across the universe, it gathers and shapes, slows and binds, yet on the grandest scales, it does not halt the expansion. The delicate balance between what we can measure and what remains hidden offers a window into the larger story of cosmic fate. By studying the tug of gravity against expansion, scientists built models of the universe's destiny, developed the concept of critical density, and laid the groundwork for confronting one of the greatest puzzles in modern science: why the universe is not slowing as expected, and what invisible force might be accelerating its growth. As scientists continued to observe distant galaxies, they turned their attention to a particular kind of stellar explosion called Type Ia supernova. These supernovae occur when a white dwarf, a dense remnant of a star, accumulates matter from a companion star until it reaches a critical mass and undergoes a violent explosion. This type of supernova is remarkable because it produces nearly the same brightness every time, regardless of its location in the universe. For astronomers, this makes Type Ia supernova a reliable marker, a standard candle that can be used to measure distances across the vast reaches of space. By comparing how bright the explosion appears from Earth to how bright it actually is, scientists can calculate how far away the supernova lies. The combination of brightness and redshift allows researchers to trace the expansion history of the universe over billions of years. In the 1990s, two research teams independently set out to measure the expansion of the universe using these supernovae. One was the Supernova Cosmology Project, and the other, the High Z Supernova Search Team. Their goal was simple yet ambitious: determine whether the expansion of the universe was slowing due to gravity, as predicted by earlier theories. Both teams measured the redshift and brightness of dozens of distant Type Ia supernovae, carefully accounting for factors that might affect their observations, such as dust in interstellar space, variations in supernova behavior, and the motion of the host galaxies. Every data point was analyzed with precision, as small errors could lead to large differences in conclusions. As the results accumulated, the scientists noticed something unexpected. The distant supernovae were fainter than anticipated. According to models where gravity gradually slows expansion, these explosions should have appeared brighter, since the galaxies hosting them would have been closer in a universe decelerating under the pull of matter. Instead, the observations suggested that the galaxies were farther away than predicted. This implied that the expansion of the universe was not slowing down at all. In fact, it was accelerating. The conclusion was so surprising that scientists initially questioned the data, looking for possible errors, biases, or unknown effects that might account for the discrepancy. Yet repeated measurements, independent analyses, and careful scrutiny confirmed the result. The universe was growing faster over time, and the force driving this acceleration was invisible and unlike anything known. The acceleration of the universe presented a profound challenge to the understanding of cosmology. Gravity, which pulls matter together, could not explain this outward push. Something else, something not directly observable must be responsible. Scientists needed a term to describe this mysterious component of the cosmos, and they coined it dark energy. Dark energy, by its nature, does not emit, absorb, or reflect light, making it impossible to detect directly with traditional telescopes. Its existence is inferred only through its effects on the expansion of space. By studying the motion of galaxies and the light from supernovae, researchers can measure the influence of dark energy, even if its true nature remains unknown. Early interpretations of dark energy varied. Some scientists suggested it might be related to the vacuum of space itself. In quantum physics, even empty space is not truly empty. It is filled with fleeting energy fluctuations, tiny events that arise and vanish continuously. This vacuum energy could, in theory, exert a repulsive effect, pushing space outward and causing acceleration. Others proposed that dark energy might be a new dynamic field permeating the universe, changing slowly over time. Some researchers speculated about modifications to the laws of gravity at cosmic scales, though these ideas faced significant challenges in matching observations. What remained clear was that the discovery of acceleration marked a turning point in cosmology, revealing that the universe is governed by forces beyond ordinary matter and gravity. The scale of dark energy's influence is immense. Observations indicate that it dominates the energy content of the universe, accounting for roughly 68% of the total. Ordinary matter, the stars, planets, gas, and dust familiar to us, makes up only about 5%, while dark matter, another unseen component that interacts through gravity, contributes about 27%. Dark energy's dominance explains why the expansion has not slowed, despite the pull of gravity from galaxies and clusters. Its effect is uniform, acting throughout space, causing distant galaxies to recede from each other faster over time. The concept challenges intuition, as it suggests that most of the universe is composed of something invisible, yet overwhelmingly powerful. The discovery of accelerating expansion also reshaped predictions about the universe's future. If dark energy continues to dominate, galaxies will move away from each other ever more rapidly. Light from distant galaxies will stretch, becoming fainter and redder, eventually leaving observers in any one galaxy with only a local view of the cosmos. This scenario implies a cold, sparse, and ever-expanding universe, sometimes referred to as the Big Freeze. The future cosmos, governed by dark energy, would be vastly different from the early dense universe in which galaxies formed. Understanding the properties of dark energy is therefore not only about explaining the present, but also about predicting the long-term evolution of everything in existence. Observational evidence beyond Type Ia supernovae has reinforced the reality of dark energy. Measurements of the cosmic microwave background, the faint afterglow of the Big Bang, show patterns that imply a flat universe with an energy budget dominated by an unknown component. Surveys of galaxy distributions reveal large-scale structures and voids shaped not only by gravity, but also by the accelerating expansion. Baryon acoustic oscillations, subtle imprints of sound waves from the early universe, provide another method to map cosmic expansion over time. Across multiple independent lines of evidence, the conclusion is consistent. A mysterious force drives the universe outward, unseen yet detectable through its effects on space and matter. Despite the compelling evidence, the nature of dark energy remains elusive. Scientists continue to test hypotheses, using increasingly precise measurements and sophisticated instruments. Observatories on Earth and in space track the positions, distances, and velocities of galaxies. Telescopes map the distribution of matter and measure subtle distortions caused by gravity. Experiments probe the properties of supernovae, the cosmic microwave background, and large-scale structures. The goal is to understand the equation of state of dark energy, a parameter that describes how it behaves over time and influences cosmic expansion. Each observation refines models and narrows the possibilities, yet the fundamental origin of dark energy remains one of the greatest mysteries in science. The discovery of acceleration also underscores the importance of observational persistence and careful methodology. Measuring faint supernovae, billions of light-years away, requires not only sensitive instruments, but also meticulous attention to detail. Variations in brightness, interference from cosmic dust, and local motion of galaxies must all be accounted for. Teams of scientists cross-check results, analyze data independently, and apply corrections to ensure reliability. The acceleration of the universe was not found overnight. It emerged from years of patient observation, analysis, and verification. The process exemplifies the rigor of scientific inquiry and the challenges of studying phenomena on the grandest scales. In reflecting on the accelerating universe, it is clear that dark energy reshapes our understanding of reality. The universe is not slowing under the familiar pull of gravity, but expanding faster than ever. Space itself carries galaxies apart, driven by an unknown influence that pervades all of existence. The cosmic landscape is dynamic and surprising, governed by laws that continue to reveal deeper layers of complexity. Observing supernovae, mapping galaxies, and measuring subtle cosmic signals are not merely technical exercises. They are windows into the profound structure of the cosmos, revealing a universe that is stranger and more wondrous than imagination alone could conceive. The story of acceleration reminds us of the scale of the universe and our role within it. The force of dark energy operates across billions of light-years, beyond the reach of human senses, yet its effects are measurable and undeniable. By studying these distant phenomena, scientists connect the present with billions of years of cosmic history, tracing the evolution of space itself. Each supernova observed, each galaxy mapped, contributes to a growing understanding, even as many questions remain unanswered. The universe, vast and ever-expanding, continues to challenge, to surprise, and to inspire, inviting us to observe, measure, and reflect on the invisible forces that shape reality. Dark energy is now understood to be the dominant component of the universe, making up roughly 68% of all energy in existence. It is not something we can see or touch. Unlike stars, planets, or gas, dark energy does not interact with light or ordinary matter in ways we can detect directly. Its presence is inferred entirely from its effect on the expansion of space. While ordinary matter, the atoms and molecules that form everything familiar to us, constitutes about 5% of the universe, and dark matter, which influences gravity but remains invisible, makes up around 27%. Dark energy governs the large-scale motion of galaxies and the overall growth of the cosmos. This dominance means that, although it is intangible and elusive, dark energy shapes the universe in fundamental ways. Dark energy is fundamentally different from dark matter. Dark matter has mass, and it exerts gravitational pull. It clumps together, forming halos around galaxies and influencing the motion of stars and galaxies within clusters. We detect dark matter indirectly through its gravitational effects on visible matter and the bending of light known as gravitational lensing. Dark energy, in contrast, acts as a repulsive force, pushing space outward. It does not clump or form structures. Instead, it is uniform, spread evenly throughout space, and its effect grows more noticeable as distances increase. The farther apart galaxies are, the stronger the effect of dark energy in causing them to move away from each other faster over time. While dark matter pulls, dark energy pushes, and together they create the complex dance of cosmic motion we observe. Observational evidence for dark energy comes from multiple sources. Type R supernovae, as described earlier, provide a direct way to measure how fast the universe is expanding at different times. By observing these explosions in distant galaxies and comparing their brightness to closer examples, astronomers can reconstruct the expansion history. The surprising result, that distant supernovae appear dimmer than expected, led to the realization that expansion is accelerating, a key indication of dark energy's presence. These measurements alone were compelling, but scientists sought confirmation through independent methods to strengthen their conclusions. One major source of evidence is the cosmic microwave background, or CMB. The CMB is the faint afterglow of the Big Bang, radiation left over from the early universe when it was hot, dense, and nearly uniform. Careful measurements of the CMB reveal tiny fluctuations in temperature and density, which carry information about the composition and evolution of the universe. Observatories such as the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite mapped these fluctuations with extraordinary precision. The patterns in the CMB indicate a flat geometry for the universe, meaning that the total energy density is very close to the critical value needed to balance expansion and gravity. The contribution from ordinary matter and dark matter alone falls short, implying that an additional component, dark energy, must account for the remaining energy required to maintain this flatness. Another line of evidence comes from the large-scale structure of the universe. Galaxies are not distributed randomly, but form a vast cosmic web of filaments, clusters, and voids. The formation and evolution of these structures are influenced by the expansion of space and the gravitational pull of matter. Observing the distribution of galaxies at different distances allows astronomers to trace how structure has grown over time. The patterns observed match models that include dark energy as a uniform, repulsive force driving accelerated expansion. Surveys like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, have mapped millions of galaxies, providing a three-dimensional picture of the universe and confirming the influence of dark energy on cosmic growth. Baryon acoustic oscillations, subtle ripples left over from pressure waves in the early universe, offer yet another method to study dark energy. These ripples are imprinted in the distribution of galaxies and serve as a standard ruler for measuring distances. By comparing the observed scale of these features at different epochs, scientists can determine the rate at which the universe has expanded. The measurements align closely with the accelerating expansion inferred from supernova observations and the CMB, reinforcing the conclusion that dark energy is real and influential. Each method is independent, yet they converge on the same story. The universe is dominated by a component that drives it outward, invisible but measurable through its effects. Dark energy is not uniform in its manifestation, but constant in its influence. The simplest explanation is the cosmological constant, a term introduced by Einstein in his equations of general relativity. This constant represents an intrinsic energy of empty space, a fixed value that causes repulsion on large scales. If this interpretation is correct, dark energy does not change over time. It has been pushing space outward steadily since the early universe. Observations so far are consistent with this model, though slight deviations could indicate more complex behaviors. Scientists continue to examine whether dark energy is truly constant or if it might vary slowly, a possibility that would point to dynamic fields rather than a fixed property of space. While the evidence for dark energy is strong, its nature remains a mystery. Physicists have attempted to calculate the energy density of empty space using quantum mechanics, predicting values that are far larger than observed. The discrepancy between theoretical predictions and actual measurements is enormous, highlighting a gap in understanding. Dark energy does not behave like ordinary matter or radiation, and no laboratory experiment has yet been able to reproduce or probe it directly. Its existence is inferred only through large-scale observations of galaxies, cosmic background radiation, and the growth of structure, making it both familiar and profoundly strange. Despite these challenges, understanding dark energy is essential for explaining the universe's evolution. Its presence affects not only the current expansion, but also the future of cosmic structures. Galaxies that are gravitationally bound, like those in our local group, remain together, but more distant galaxies will recede faster and eventually move beyond our observable horizon. Over billions of years, dark energy will determine the pace at which the universe grows, shaping the large-scale geometry and influencing the conditions for any potential future observations. Studying it allows scientists to anticipate cosmic evolution and refine models of fundamental physics. The uniformity of dark energy is also remarkable. Unlike matter, which can cluster and form dense regions, dark energy acts equally everywhere. Its repulsive effect does not depend on local conditions, but on the presence of space itself. As the universe expands and regions grow farther apart, the influence of dark energy becomes more prominent, gradually overpowering the gravitational pull of matter on the largest scales. This balance between attraction and repulsion defines the dynamics of galaxies, clusters, and the intergalactic medium, illustrating how a force that cannot be seen directly can dominate the behavior of the cosmos. Observing dark energy is an ongoing effort, requiring precise and long-term measurements. Astronomers track supernovae, map the cosmic microwave background, and analyze galaxy distributions to understand how expansion evolves. Every new observation improves constraints on the density, behavior, and properties of dark energy. Future telescopes and surveys are expected to refine these measurements further, revealing whether dark energy is a simple cosmological constant or a dynamic field with subtle variations. Each piece of data contributes to a growing picture of the universe's composition and expansion history, building a coherent story from the faint signals traveling across billions of light-years. In examining dark energy in detail, it is clear that we are confronting a force unlike any other. It is invisible, pervasive, and dominant, shaping the universe in ways that ordinary matter cannot. Observations from supernovae, the cosmic microwave background, and large-scale structure consistently point to its presence, even as its true nature remains hidden. Dark energy challenges intuition, requiring new ways of thinking about space, motion, and the evolution of the cosmos. By studying its effects, scientists gain insight into both the current state of the universe and its future trajectory, revealing a vast, accelerating cosmos governed by a mysterious and powerful influence. The concept of a cosmological constant was first introduced by Albert Einstein in the early 20th century. When he formulated his general theory of relativity, Einstein aimed to describe the universe as static, neither expanding nor contracting. Gravity, as described by his equations, would naturally cause all matter to pull together, leading to eventual collapse. To prevent this, he added a term to his equations called the cosmological constant, symbolized by the Greek letter lambda. This constant acted as a repulsive force, counteracting gravity and allowing the universe to remain unchanging. At the time, this idea seemed artificial, a mathematical adjustment to match the expectation of a steady cosmos. Yet the discovery of the universe's expansion decades later demonstrated that the cosmological constant might describe a real physical phenomenon, one that pushes space outward. Modern cosmology interprets the cosmological constant as a form of vacuum energy. Even empty space, devoid of stars, planets, and gas, is not truly empty. Quantum physics predicts that space is filled with temporary energy fluctuations, tiny bursts of energy that appear and disappear constantly. This energy contributes to the overall dynamics of the universe. In the context of general relativity, vacuum energy has a repulsive effect on space, causing it to expand. If the vacuum energy has a constant value everywhere, it produces the effects described by the cosmological constant. This interpretation aligns with observations showing that the universe's expansion accelerates, and that dark energy appears uniform and pervasive across all of space. Despite this appealing explanation, the value of vacuum energy predicted by quantum theory is far larger than what is observed. Calculations suggest a density of empty space many orders of magnitude higher than the small but measurable value inferred from cosmic expansion. This enormous discrepancy is known as the cosmological constant problem. It is one of the greatest puzzles in theoretical physics, highlighting a mismatch between quantum mechanics and cosmology. Scientists continue to search for mechanisms that could reduce the effective energy density of the vacuum to match observations. The challenge demonstrates that while the cosmological constant provides a simple description, understanding the underlying physics remains an open question. Alternative theories of dark energy explore the possibility that it is not constant, but dynamic. One idea is called quintessence, a hypothetical field that varies slowly over time and space. Unlike a cosmological constant, quintessence can change in density and strength, potentially evolving as the universe grows. Models of quintessence suggest that the force driving acceleration might have been weaker or stronger in the past, leaving subtle imprints on the cosmic microwave background, the growth of structure, and the expansion history measured through supernovae. Observations aim to detect these variations, providing evidence for or against dynamic models. But so far, results are consistent with a constant dark energy, though small deviations cannot yet be ruled out. Another possibility is that gravity itself behaves differently on the largest scales. Modified gravity theories propose changes to general relativity that become significant across billions of light-years. These modifications could mimic the effects of dark energy, producing accelerated expansion without introducing a new energy component. Testing these ideas requires comparing predictions with observations of cosmic expansion, galaxy clustering, and gravitational lensing. So far, standard general relativity with a cosmological constant provides the simplest and most consistent match to observations, but alternative models remain under consideration. They offer insight into how fundamental laws of physics might operate differently in extreme, large-scale environments. Scientists use multiple observational approaches to evaluate cosmological models. Supernova measurements reveal how expansion changes over time. The cosmic microwave background provides constraints on the total energy density, geometry, and composition of the universe. Surveys of large-scale structure trace the distribution and growth of galaxies, providing further evidence for the balance between attraction and repulsion. Combining these lines of evidence allows researchers to refine the parameters of cosmological models, determining whether dark energy behaves like a cosmological constant, varies dynamically, or could be explained by modified gravity. Each piece of data contributes to a complex, interconnected picture, where theory and observation continually inform each other. The interplay between theory and observation is delicate. Observational precision has increased dramatically in recent decades, requiring instruments capable of detecting extremely faint light from distant galaxies, mapping minute temperature variations in the cosmic microwave background, and tracking the motion of billions of stars. At the same time, theoretical models must account for quantum effects, general relativity, and large-scale structure formation. Adjusting a model to match one set of observations can affect predictions elsewhere, so scientists work carefully to maintain consistency across all evidence. The process illustrates the dynamic nature of science, where hypotheses are constantly tested, refined, and sometimes rejected in light of new information. The cosmological constant also has implications for the future of the universe. If dark energy is constant, the acceleration of expansion will continue indefinitely. Galaxies beyond the local group will recede beyond our ability to observe them, and the observable universe will shrink in a practical sense. Over trillions of years, stars will burn out, galaxies will fade, and the cosmos will become increasingly cold and dark. In this view, the cosmological constant provides a framework for understanding long-term evolution, linking the physics of empty space to the fate of everything in existence. Alternative models, such as quintessence or modified gravity, offer different scenarios, but all underscore the critical role of dark energy in shaping the universe. Vacuum energy, quintessence, and modified gravity illustrate the breadth of theoretical exploration. Scientists must consider fundamental physics, observational constraints, and consistency across scales, from the quantum to the cosmic. The cosmological constant provides a simple and effective description, but it is only one piece of a larger puzzle. Exploring alternatives helps identify where gaps in understanding remain and guides the design of new observations and experiments. Each model offers testable predictions, creating a roadmap for future inquiry and ensuring that cosmology remains an evolving science, responsive to both data and theory. The challenge of matching theory with observation also emphasizes the subtlety of cosmic measurements. Measuring expansion, density, and acceleration involves interpreting faint signals across vast distances and times. Instruments must correct for dust, gravitational lensing, and motion within galaxies and clusters. The light from a galaxy billions of light-years away shows its state from billions of years ago, requiring careful reconstruction of history. Small errors can propagate, influencing conclusions about dark energy's behavior. Scientists address this with repeated measurements, independent teams, and statistical methods to ensure reliability. Through patient effort, theory and observation come into alignment, revealing the universe's underlying dynamics. Ultimately, the cosmological constant and its alternatives represent humanity's attempt to describe an invisible force that governs the cosmos. The simple term Einstein added to his equations has grown into a profound exploration of vacuum energy, dynamic fields, and possible modifications to fundamental laws. Observations of supernovae, the cosmic microwave background, and large-scale structure provide a clear, consistent indication that the universe is accelerating. Matching this evidence to theory is an ongoing challenge, bridging quantum physics, relativity, and cosmology. The result is a story of discovery, refinement, and deepening understanding, highlighting how invisible forces shape the universe in ways both subtle and immense. Observing dark energy requires careful measurement of the universe over immense distances and times. Because dark energy cannot be seen or touched, scientists rely on its effects, particularly the way it accelerates the expansion of space. One of the most direct methods uses Type Ia supernovae. These stellar explosions serve as standard candles, objects of known brightness that allow astronomers to calculate distances across billions of light-years. By measuring the redshift of a supernova's light and comparing it to its apparent brightness, researchers determine how far away the host galaxy is and how fast it is receding. Repeating this for many supernovae at different distances builds a picture of how the expansion of the universe has changed over time, revealing the influence of dark energy. Beyond supernova, astronomers use another method called baryon acoustic oscillations. In the early universe, pressure waves propagated through hot plasma, leaving subtle imprints in the distribution of matter. As the universe cooled and neutral atoms formed, these ripples became frozen in the distribution of galaxies, acting as a standard ruler. By mapping the spacing of galaxies and comparing it to the expected scale of these ripples, scientists can infer the expansion history of space. Baryon acoustic oscillations provide a complementary method to supernovae, relying on a different kind of measurement and offering independent confirmation of cosmic acceleration. Together, these two methods strengthen the evidence for dark energy and allow for more precise estimates of its properties. Large-scale galaxy surveys are another critical approach. Projects like the Sloan Digital Sky Survey and the Dark Energy Survey map the positions and shapes of millions of galaxies, creating three-dimensional maps of the universe. These maps reveal the cosmic web, the network of filaments, clusters, and voids that stretch across hundreds of millions of light-years. By studying how these structures grow and evolve over time, scientists can infer the influence of dark energy on the expansion of space. The patterns observed are consistent with models that include a dominant, uniform energy component driving acceleration, while the distribution of dark matter and ordinary matter explains the formation of structures within this expanding framework. Space telescopes have played a central role in observing dark energy. The Hubble Space Telescope has provided detailed images of distant galaxies and supernovae, enabling precise distance measurements and redshift calculations. Hubble's sensitivity to faint light allows astronomers to detect supernova billions of light-years away, providing a window into the universe's expansion billions of years in the past. Similarly, the WMAP and Planck satellites have measured the cosmic microwave background with remarkable precision, mapping tiny temperature fluctuations that encode information about the universe's geometry, energy composition, and early growth. These observations have constrained the proportion of dark energy, dark matter, and ordinary matter, confirming that dark energy dominates the energy budget of the cosmos. Ground-based observatories also contribute significantly. The Dark Energy Survey, conducted from the Cerro Tololo Inter-American Observatory in Chile, uses wide-field imaging to map hundreds of millions of galaxies. By measuring their positions, shapes, and redshifts, DES tracks the growth of large-scale structure over time. Observing weak gravitational lensing, the bending of light by matter along the line of sight, provides another method to probe the distribution of dark matter and the expansion rate. Ground-based telescopes complement space-based instruments, offering larger fields of view and the ability to survey vast areas of the sky systematically, though atmospheric effects limit some measurements. Together, space and ground observatories provide a comprehensive approach to observing dark energy. Precision in measurement is crucial because dark energy's effects, while pervasive, are subtle. The expansion of space is accelerated, but the change occurs gradually over billions of years. Detecting this requires not only sensitive instruments, but also careful calibration, control of systematic errors, and repeated observations. Photometric errors, dust in galaxies, variations in supernova brightness, and distortions caused by gravitational lensing must all be accounted for. Scientists apply statistical methods, cross-check results, and combine data from multiple surveys to ensure that conclusions are reliable. Each improvement in precision brings the possibility of refining models, distinguishing between a constant cosmological constant and dynamic dark energy, or even testing alternative theories of gravity. The combination of methods creates a robust framework for studying dark energy. Type Ia supernovae measure expansion directly by comparing distance and redshift. Baryon acoustic oscillations provide a scale for space itself, while galaxy surveys track the growth of structure under the influence of gravity and expansion. Measurements of the cosmic microwave background offer constraints on the total energy density and geometry of the universe. Each approach tests different aspects of cosmology, yet all converge on the same conclusion. A mysterious dominant component is driving accelerated expansion. The convergence of independent methods gives scientists confidence in the existence of dark energy, despite its invisibility and elusiveness. Observing dark energy also requires careful planning and long-term monitoring. Supernovae surveys must revisit the same regions of the sky repeatedly, catching explosions at the right moment and following their brightness over time. Galaxy surveys involve cataloging millions of objects, measuring redshifts through spectroscopy or photometry, and tracking subtle patterns in distribution and shape. Cosmic microwave background experiments must eliminate noise from foreground sources, such as dust and emission from the Milky Way. Each type of observation demands patience, precision, and consistency, reflecting the scale and subtlety of the phenomena being studied. Limitations in measurement present ongoing challenges. Observing faint light from distant objects pushes telescopes to their limits. Atmospheric distortion, instrumental calibration, and cosmic variance, the fact that we can observe only one realization of the universe, introduce uncertainties. Interpreting the data requires careful modeling and statistical analysis, ensuring that the inferred properties of dark energy are robust. As instruments improve and surveys expand, the ability to test the properties of dark energy becomes more refined, allowing scientists to constrain models more tightly and explore whether dark energy behaves as a simple cosmological constant or varies with time and space. The observation of dark energy illustrates the interplay between technology, theory, and patience. Instruments like Hubble, Planck, WMAP, and DES provide the data. Theoretical models interpret the results, offering explanations and predictions, and careful methodology ensures that conclusions are reliable. Observing the universe on such vast scales across billions of light years demonstrates both the challenges of cosmology and the ingenuity required to meet them. Each measurement, whether of a distant supernova, a ripple in galaxy distribution, or a subtle temperature variation in the CMB, contributes to the growing understanding of the dominant force shaping cosmic expansion. Through these observational efforts, scientists have confirmed that dark energy exists, acts uniformly across space, and drives the accelerated expansion of the universe. While its nature remains mysterious, its effects are measurable, consistent, and profound. Observing dark energy provides a bridge between the distant past and the present, revealing how the universe has evolved over billions of years. By combining multiple methods, astronomers can cross-check results, reduce uncertainties, and refine models, building a coherent and robust picture of the cosmos. The careful study of supernovae, baryon acoustic oscillations, and galaxy surveys continues to reveal the invisible, dominant force shaping the universe on the grandest scales. Each observation adds context to the story of cosmic acceleration. Supernova illuminate the distances and speeds of galaxies. Galaxy surveys map the scaffolding of matter shaped by gravity. Baryon acoustic oscillations offer a standard ruler frozen from the early universe. The cosmic microwave background provides a backdrop that encodes information from the universe's first moments. Together, these observations demonstrate the pervasive influence of dark energy, revealing a universe whose expansion is not slowing under gravity, but accelerating, guided by a force beyond ordinary matter. The precision and breadth of these measurements illustrate the remarkable progress made in understanding something invisible, yet overwhelmingly powerful, highlighting how human observation can uncover the hidden workings of the cosmos. The cosmic microwave background, or CMB, is one of the most important tools scientists use to understand the universe. It is the faint afterglow of the Big Bang, radiation that fills every part of space. When the universe was only a few 100,000 years old, it was hot, dense, and filled with a glowing plasma of protons, electrons, and photons. Light could not travel freely because it was constantly scattered by charged particles. As the universe expanded and cooled, neutral atoms formed, and photons began to move without constant interaction. This moment left a relic, the CMB, a snapshot of the universe at that early stage. Today, the CMB is observed as microwave radiation, with a nearly uniform temperature of about 2.7 Kelvin, just above absolute zero. Tiny variations in this temperature, only a few parts in 100,000, contain a wealth of information about the composition, structure, and history of the cosmos. Measuring these minute fluctuations requires instruments of exceptional sensitivity. The WMAP and Planck satellites have mapped the CMB with remarkable precision, revealing patterns that reflect the density variations present in the early universe. Hotter regions correspond to slightly denser areas, where matter would eventually cluster to form galaxies and larger structures. Colder regions indicate less dense areas that would evolve into cosmic voids. By analyzing these variations, scientists can determine the proportion of ordinary matter, dark matter, and dark energy, as well as the overall geometry of space. The CMB acts as a cosmic blueprint, showing the initial conditions from which the universe grew, and highlighting the influence of unseen forces like dark energy on large-scale expansion. The geometry of the universe can be inferred from the angles of the fluctuations in the CMB. If the universe is flat, as measurements indicate, the total energy density equals the critical density needed to balance expansion and gravity. This balance requires the presence of dark energy, as ordinary and dark matter alone are not sufficient to produce a flat geometry. Slight deviations in geometry would change the apparent size of the fluctuations, making them appear larger or smaller than expected. Observations consistently show a flat universe, suggesting that dark energy fills the missing portion of the energy budget. This information links the earliest observable light to the behavior of space today, providing a powerful constraint on cosmological models. The tiny variations in the CMB also inform how structure forms over time. Regions of higher density attract surrounding matter, growing into filaments, clusters, and superclusters of galaxies. Lower density regions become vast voids with very little matter. As the universe expands, these patterns stretch, and dark energy plays a critical role by accelerating the expansion between dense regions. This acceleration affects how structures evolve, slowing the rate at which matter collapses in certain regions and influencing the large-scale arrangement of galaxies. The interplay between gravity pulling matter together and dark energy pushing space apart shapes the cosmic web we observe today. Galaxy surveys reveal the distribution of matter across billions of light-years, confirming the patterns predicted by the CMB. Galaxies are not randomly scattered, but form interconnected filaments and sheets, separated by large empty voids. This cosmic web resembles a vast three-dimensional network stretching across the observable universe. Clusters of galaxies form at the intersections of filaments, where density is highest, while voids occupy the largest regions, nearly devoid of galaxies. Observing the cosmic web allows scientists to understand how initial density variations evolved under the influence of gravity and dark energy, linking early universe conditions to present-day structure. The size, shape, and connectivity of filaments provide clues about the universe's expansion and the properties of dark energy. Simulations of structure formation use known physics to model how matter clumps over time, starting from the density variations seen in the CMB. Comparing these simulations with observed structures allows scientists to test the effects of dark energy on cosmic growth. If dark energy was stronger or weaker, the filaments, clusters, and voids would have different patterns. The match between simulations and observations supports current models, indicating that dark energy has a nearly constant effect across space and time, dominating the expansion on the largest scales while allowing gravity to shape smaller structures. Voids, the vast empty spaces between filaments, are also important for studying cosmic expansion. They expand more rapidly than dense regions, and their growth rate is influenced by dark energy. Observing voids provides an independent measure of how the universe expands, complementing supernovae, baryon acoustic oscillations, and galaxy surveys. By tracking voids at different distances, astronomers can study the acceleration of expansion over time, confirming that dark energy acts uniformly across the universe. The combination of dense filaments and expansive voids illustrates the balance between gravity and dark energy in shaping the cosmos. The cosmic web also influences galaxy evolution. Galaxies in dense filaments tend to interact more frequently, merging or exchanging material, while those in isolated regions evolve more slowly. The arrangement of galaxies in clusters and filaments provides information about the gravitational effects of both visible and dark matter. Mapping these structures and understanding their growth allows scientists to reconstruct the history of matter distribution and the influence of dark energy throughout cosmic time. Large-scale surveys produce detailed three-dimensional maps, capturing millions of galaxies and tracing the intricate web that spans the observable universe. In addition to galaxy distributions, the CMB provides constraints on dark energy through the integrated Sachs-Wolf effect. As photons from the CMB travel through large-scale structures, the gravitational potential wells they encounter change over time due to the influence of dark energy. This alters the energy of the photons slightly, producing subtle temperature variations in the CMB. Measuring these changes offers another way to detect the effect of dark energy on the expansion of space and the growth of structure. Although these signals are faint, they add a crucial piece to the puzzle, connecting the behavior of light from the earliest universe to the acceleration observed in galaxies billions of years later. The study of the cosmic microwave background and large-scale structure together provides a consistent, coherent picture of the universe. The CMB gives the initial conditions, showing the density variations and overall energy composition. Galaxy surveys map how these variations evolved into the cosmic web of filaments, clusters, and voids. Observations of void, growth, filament connectivity, and galaxy clustering test the effects of dark energy and confirm its dominant role in cosmic expansion. Each line of evidence reinforces the others, demonstrating that the universe is not only expanding, but doing so at an accelerating rate, influenced by a force that is uniform, invisible, and pervasive across space. Through these observations, scientists gain insight into both the origin and the evolution of the universe. The patterns in the CMB link the first light to the distribution of galaxies today, revealing how the interplay of gravity, matter, and dark energy has shaped cosmic history. Filaments, voids, and clusters trace the flow of matter under these forces, while dark energy continues to accelerate the expansion of space. By studying these structures, astronomers can test theoretical models, refine estimates of cosmic parameters, and deepen understanding of the universe's composition. The cosmic microwave background and large-scale structure together create a window into the invisible architecture of the cosmos, illustrating the remarkable balance between the seen and the unseen, the familiar and the mysterious. One of the most intriguing aspects of dark energy lies in its connection to the quantum vacuum. In the microscopic world, even empty space is never truly empty. Quantum theory predicts that particles and antiparticles constantly appear and disappear, a phenomenon known as vacuum fluctuations. These fluctuations carry energy, called zero-point energy, and they exist everywhere, even in the absence of matter or light. The idea that empty space itself can have energy seems counterintuitive, but quantum mechanics demonstrates that the vacuum is a dynamic, seething medium full of transient events. This energy contributes to the dynamics of the universe and provides a potential explanation for dark energy, though the details are far from simple. The problem arises when physicists attempt to calculate the expected energy of the vacuum. Using quantum field theory, the sum of all possible fluctuations produces an enormous value for vacuum energy, many orders of magnitude greater than what is observed through cosmic expansion. Observations show that dark energy density is extremely small, yet non-zero, leading to a striking mismatch between theory and measurement. This discrepancy is known as the cosmological constant problem. It is one of the greatest unsolved puzzles in physics because it highlights a tension between our understanding of the quantum world and the large-scale structure of the universe. The predicted vacuum energy is so large that if it were real, the universe would have expanded far too rapidly for galaxies, stars, or planets to form. Scientists have proposed various explanations for why this discrepancy exists. Some theories suggest that an unknown mechanism cancels out most of the vacuum energy, leaving only a tiny residual that drives cosmic acceleration. Others explore dynamic fields, such as quintessence, which might vary over time and space, producing the small observed effect. Despite decades of work, no solution has yet gained consensus. The mystery of why the vacuum energy is small but non-zero remains a profound challenge, revealing the limits of current understanding and the deep connection between the microscopic quantum world and the vast cosmic landscape. Adding to the complexity is the Hubble tension, a recent discrepancy in measurements of the universe's expansion rate. The Hubble constant describes how fast galaxies move away from us per unit of distance. Observations using the cosmic microwave background, interpreted through models including dark energy, give one value. Direct measurements using supernova and Cepheid variable stars produce a slightly higher value. This tension suggests that either there are unknown systematic errors in measurements or that new physics might be involved, possibly connected to dark energy or the behavior of space at large scales. Resolving the Hubble tension is crucial for understanding the true nature of dark energy and refining models of cosmic expansion. The connection between the quantum vacuum and cosmic acceleration illustrates the strange bridge between the very small and the very large. Fluctuations that occur on microscopic scales could, in principle, influence the motion of galaxies billions of light-years apart. Yet the calculations fail to match reality, leaving an enormous gap in comprehension. Scientists are exploring whether new physics, unknown symmetries, or yet undiscovered particles could explain why vacuum energy appears so small. Observations of the universe on the largest scales, combined with insights from quantum theory, are essential for testing these ideas and refining models of dark energy. The mystery is compounded by the fact that dark energy dominates the universe's energy content, but interacts weakly, if at all, with matter. Unlike dark matter, which reveals itself through gravity and lensing, or ordinary matter, which can be seen and measured, dark energy is inferred solely through its effect on the expansion of space. Its presence is subtle, yet profound. Understanding how such a pervasive component can remain invisible and yet shape cosmic evolution is a challenge that connects cosmology, quantum mechanics, and fundamental physics. The solution may require new principles or modifications to current theories, suggesting that our understanding of nature is still incomplete. The Hubble tension, in particular, emphasizes the need for precise and varied observations. Measuring the expansion rate directly involves tracking nearby galaxies using standard candles, while indirect methods rely on modeling the early universe and extrapolating its evolution. The mismatch raises questions about the assumptions in these models and whether unknown processes influenced the expansion history. Dark energy plays a central role, as any new understanding of its properties could affect calculations of the Hubble constant. Resolving this tension may provide insight into whether dark energy is a cosmological constant, a dynamic field, or something entirely unexpected. Researchers are also investigating whether dark energy could change over time. A dynamic vacuum, slowly evolving, could leave subtle imprints on the cosmic microwave background, the distribution of galaxies, or the expansion rate at different epochs. Detecting such changes requires long-term, precise measurements across multiple methods, combining supernova surveys, galaxy mapping, and microwave background analysis. Observing a change would challenge the cosmological constant model and provide new clues about the quantum nature of space and energy. The universe itself becomes a laboratory for testing fundamental physics, revealing phenomena that cannot be reproduced in terrestrial experiments. Despite these uncertainties, the study of vacuum energy and the Hubble tension drives scientific progress. By confronting the mismatch between theory and observation, physicists refine calculations, explore alternative models, and develop innovative observational techniques. Each attempt to reconcile quantum predictions with cosmic measurements deepens understanding, even if a complete solution remains out of reach. The challenge of explaining dark energy highlights the need for interdisciplinary approaches, combining cosmology, particle physics, and quantum mechanics to tackle the most fundamental questions about the universe. The quantum vacuum also illustrates the limits of human intuition. Empty space is not truly empty, yet it behaves in ways that influence galaxies and the largest cosmic structures. The energy of the vacuum, while invisible, exerts a repulsive force, pushing space outward. This subtle, pervasive influence shapes the evolution of the universe over billions of years, demonstrating that phenomena at the smallest scales can have consequences on the largest scales imaginable. Scientists must navigate this complex interplay, using observations of distant light and matter to infer the behavior of a component that cannot be touched or directly observed. In the face of these mysteries, cosmologists continue to gather data, refine models, and test predictions. Instruments capable of measuring faint light from distant galaxies, mapping the cosmic microwave background, and tracing the growth of structure provide constraints on the properties of dark energy. Observing voids, filaments, and galaxy clusters allows researchers to test whether acceleration has been constant or changing over time. Each measurement narrows possibilities, gradually building a picture of how dark energy interacts with the universe. Even small improvements in precision can provide crucial insight into the connection between quantum fluctuations, vacuum energy, and cosmic acceleration. Ultimately, the quantum vacuum and the Hubble tension reveal that the universe is stranger than it first appears. Dark energy dominates the cosmos, invisible yet profoundly influential, and our understanding of its origin remains incomplete. Reconciling theoretical predictions with observations, explaining the small but non-zero vacuum energy, and resolving tensions in expansion measurements are central challenges in modern cosmology. By studying the universe from its earliest light to its largest structures, scientists confront the delicate balance between the microscopic and the cosmic, exploring how the invisible forces of the vacuum shape everything from galaxies to the overall expansion of space. Each step forward brings us closer to understanding one of the deepest mysteries in science, showing that even in the vast emptiness of space, the laws of physics continue to reveal unexpected complexity and subtle beauty. The study of dark energy is far from complete. Observations so far have confirmed its presence, measured its effects, and refined models of cosmic expansion, but its true nature remains elusive. To move forward, scientists are planning a new generation of experiments and telescopes designed to probe dark energy with unprecedented precision. These missions aim to map the universe more comprehensively, track the growth of structure in finer detail, and measure how the expansion rate changes over time. By combining multiple methods and observations, researchers hope to answer fundamental questions about whether dark energy is constant, dynamic, or indicative of new physics. The European Space Agency's Euclid mission is one such effort. Scheduled for launch in the coming years, Euclid will carry a wide-field telescope into space, avoiding atmospheric distortions that limit ground-based observations. Its primary goal is to map the distribution of galaxies and dark matter over a vast volume of the universe, using weak gravitational lensing and galaxy clustering. By measuring the shapes and positions of millions of galaxies, Euclid will reconstruct the three-dimensional structure of the cosmos and observe how it evolves. This data will allow scientists to test the influence of dark energy on the growth of structure, offering insights into its properties and potential changes over time. Euclid's observations will complement previous surveys, extending the reach and precision of dark energy studies. In parallel, NASA's Nancy Grace Roman Space Telescope will provide another powerful window into cosmic acceleration. Roman will survey large areas of the sky with high resolution, targeting supernovae, galaxy clusters, and gravitational lensing. One of its key objectives is to measure the equation of state of dark energy, a parameter that describes the relationship between its pressure and density. If dark energy behaves like a cosmological constant, the equation of state remains constant at a value of -1. Deviations from this value would indicate dynamic behavior, suggesting quintessence or other alternatives. Roman's observations of distant supernovae and galaxy distributions will refine constraints on this parameter, helping scientists distinguish between different models and understand whether dark energy changes over time. The Vera C. Rubin Observatory in Chile represents a major advance in ground-based surveys. Its large mirror and wide-field camera will capture the positions and brightness of billions of stars and galaxies over 10 years of continuous observation. The observatory will conduct the legacy survey of space and time, generating a detailed time-lapse map of the sky. This survey will track supernovae, measure weak lensing signals, and map large-scale structures, providing crucial information on how matter clusters and expands under the influence of dark energy. The Rubin Observatory will complement space-based missions by covering wider areas of the sky and providing long-term monitoring, allowing subtle changes in cosmic expansion to be detected. All these missions are designed to refine the equation of state of dark energy, improving the precision of current measurements. Knowing this parameter more accurately will constrain theoretical models and help determine whether dark energy is truly constant or dynamic. Observations will also test alternative theories, such as modifications to gravity, by comparing predictions of structure growth and expansion history with empirical data. By combining information from multiple approaches, scientists can reduce uncertainties, cross-check results, and develop a coherent picture of how dark energy behaves across space and time. Each experiment contributes a piece to this global puzzle, building toward a more complete understanding. The effort to understand dark energy is inherently collaborative and global. Teams from many countries and institutions work together to design instruments, plan observations, process vast quantities of data, and interpret results. Ground-based telescopes, space missions, and theoretical models all intersect in this enterprise. Data sharing, joint analysis, and coordinated strategies allow scientists to maximize the value of each observation. No single instrument or survey can reveal all aspects of dark energy, but together they provide a multi-dimensional view of the universe's expansion and the forces shaping it. This worldwide collaboration reflects both the scale of the challenge and the human desire to understand the cosmos. Future observations will also address subtle questions about the homogeneity and isotropy of dark energy. Current data suggest it is uniform across space, but small variations, if they exist, could provide insight into its underlying nature. Surveys of galaxy clusters, voids, and filaments at different distances and epochs will test whether dark energy acts identically everywhere and has remained constant throughout cosmic history. Precise measurements of the growth of structure, combined with the cosmic microwave background and baryon acoustic oscillations, will help determine whether dark energy is truly static or evolving. These studies will push the limits of observational cosmology and refine our understanding of the universe on the largest scales. The technological demands of these missions are significant. Measuring faint light from billions of galaxies, detecting subtle distortions caused by weak lensing, and monitoring supernovae over long periods require highly sensitive instruments, stable platforms, and careful calibration. Space telescopes avoid atmospheric interference, but must endure the challenges of operating far from Earth. Ground-based observatories offer larger collecting areas and long-term monitoring, but must account for atmospheric turbulence and environmental conditions. The combination of space and ground observations provides complementary strengths, maximizing coverage, depth, and precision. Together, they allow scientists to test theoretical predictions with an unprecedented level of detail. Refining constraints on dark energy will also help resolve outstanding tensions in cosmology, such as the Hubble tension. By improving measurements of the expansion rate at different times and distances, future surveys will test whether current discrepancies reflect observational limitations, systematic errors, or unknown physical effects. Understanding these details is essential for constructing a consistent model of the universe, linking early cosmic conditions to the present and predicting future evolution. Dark energy is central to this endeavor, as its properties influence both local and large-scale measurements of cosmic expansion. Resolving these questions will require the full range of upcoming experiments working together in concert. The pursuit of dark energy also inspires new theoretical work. Observational constraints from Euclid, Roman, and the Rubin Observatory will guide models of the cosmological constant, quintessence, and alternative gravity theories. Scientists will explore which scenarios match the refined data and whether adjustments to existing physics are necessary. The iterative process between theory and observation ensures that cosmology remains a dynamic, evolving field. Each new measurement informs theory, while theoretical models help design future observations, creating a continuous cycle of discovery and refinement. This synergy exemplifies the scientific method on a cosmic scale. Ultimately, the upcoming missions represent humanity's effort to confront one of the greatest mysteries in science. Dark energy dominates the universe, shaping its expansion and fate, yet it remains invisible and poorly understood. Through careful observation, precise measurement, and global collaboration, scientists hope to uncover its properties and behavior. Euclid, the Roman Space Telescope, and the Vera C. Rubin Observatory will each contribute vital data, testing models, measuring expansion, and revealing the structure of the cosmos in exquisite detail. Together, these efforts mark a new chapter in the study of dark energy, offering the promise of deeper understanding and perhaps answers to questions that have puzzled astronomers and physicists for decades. The story of these experiments also highlights the patience, ingenuity, and coordination required in modern cosmology. It takes years of planning, decades of construction, and careful operation to gather the data needed to probe dark energy. Teams must handle enormous volumes of information, calibrate instruments to high precision, and interpret results across multiple techniques. The pursuit is meticulous and careful, reflecting the subtlety of dark energy itself. Each observation, each measurement, and each analysis contributes to a global effort that spans the planet and the skies above, showing how humanity can reach for understanding even when the subject is invisible, pervasive, and profoundly mysterious. By continuing to push observational limits, refine theoretical models, and test alternative scenarios, scientists aim to reveal the true nature of dark energy. The upcoming missions will explore the universe's expansion history, map its large-scale structure, and measure the equation of state with unprecedented accuracy. Their results will guide cosmology for decades to come, helping to answer whether dark energy is constant, dynamic, or indicative of new physics. This global effort demonstrates the power of coordinated research and the enduring curiosity that drives humanity to understand the universe, even when its most dominant forces are invisible and enigmatic. As we look across the cosmos, it is impossible not to notice the quiet power of dark energy. Though invisible and intangible, it stretches space itself, accelerating the expansion of the universe in every direction. This force is subtle, yet over billions of years, its effects accumulate, carrying galaxies farther apart and shaping the future of cosmic evolution. The universe, once thought to slow under gravity, is instead moving toward a state of increasing emptiness, with distances growing and light from distant objects gradually fading beyond reach. In this vast, unfolding landscape, dark energy dictates the rhythm of cosmic expansion, a persistent and silent presence that touches everything, yet remains unseen. The implications of this force are profound. In a universe dominated by dark energy, the large-scale structures we observe today, the filaments, clusters, and cosmic web, will continue to evolve, but at a pace shaped by acceleration. Voids will widen, filaments will stretch, and the clustering of matter will slow. Stars will form in galaxies for billions of years, but eventually the material needed for star formation will dwindle. Galaxies will drift apart, leaving vast spaces of emptiness between them. The future of the cosmos is governed by this invisible influence, and though it cannot be touched or observed directly, its imprint is everywhere, guiding the motion of all matter on the grandest scales. Observing and understanding dark energy requires patience and perspective. Light from distant galaxies takes millions or even billions of years to reach Earth, and by studying it, we look not only across space, but also back in time. Each photon carries a story of the universe's expansion, of matter moving under the push of dark energy. Observing the cosmic microwave background, mapping galaxy clusters, and measuring supernova are ways to trace this history. Every measurement brings insight into the past, and each new discovery refines predictions about the future. Dark energy is both a cosmic messenger and a cosmic actor, connecting the history of the universe to its ongoing evolution. The presence of dark energy invites reflection on scale and perspective. The universe operates on scales far beyond ordinary experience. Distances measured in millions or billions of light years, time measured in billions of years, and forces invisible to the senses govern the evolution of all that exists. Dark energy dominates over the gravity of all galaxies combined, and yet its effects are gradual and almost imperceptible in the span of human observation. This contrast between subtlety and scale offers a gentle reminder of the vastness of the cosmos and the careful work required to understand it. Patience, precision, and attention to detail are essential tools for seeing what is normally hidden. Philosophically, dark energy raises questions about existence and perception. The universe is more expansive than our senses can detect, and the dominant force shaping its destiny is one we cannot directly feel. The interplay of matter, energy, and the geometry of space challenges assumptions about the familiar, revealing a cosmos governed by principles both elegant and mysterious. Reflecting on this can evoke a sense of calm wonder. Dark energy is pervasive, steady, and uniform, operating without haste, yet over time it orchestrates the unfolding of cosmic history. This rhythm, though imperceptible day by day, can be understood through careful observation and measurement, and it provides a lens for seeing the universe as a coherent and interconnected whole. Observationally, dark energy demonstrates the power of human inquiry. Instruments across the globe and in space capture faint light from distant objects, mapping the cosmic web and measuring subtle accelerations. Satellites like Planck and WMAP reveal the patterns of the cosmic microwave background, while telescopes like Hubble, Euclid, Roman, and the Vera Rubin Observatory extend our reach into distant galaxies and supernovae. By combining these observations, scientists construct a detailed understanding of the universe's composition and expansion. Dark energy, though unseen, becomes tangible through its effects, illustrating how careful study can illuminate even the most subtle and pervasive aspects of reality. Looking forward, the future of cosmic exploration will continue to deepen this understanding. As new surveys gather more precise data and theoretical models evolve, the properties of dark energy may be revealed in greater detail. Perhaps it is a constant feature of the universe, or perhaps it varies slowly over time. Either way, its presence dictates the ultimate fate of galaxies, clusters, and the large-scale structure of the universe. By studying its influence, astronomers glimpse the long-term evolution of the cosmos, providing perspective not only on space, but on time itself, revealing the slow unfolding of cosmic history under the guidance of this invisible force. Dark energy also fosters a gentle awareness of the scale of human existence. Individual lives and even civilizations are fleeting on cosmic timescales. The universe operates over billions of years, and forces like dark energy shape epochs far beyond human observation. Yet through observation, calculation, and reflection, humans can understand these processes and connect with the broader story of the cosmos. There is a quiet satisfaction in realizing that even within such vast scales, careful study allows insight into the mechanisms governing space, time, and energy. It is a reminder of both humility and capability, the capacity to perceive and understand phenomena far larger than ourselves. The cosmic expansion driven by dark energy is continuous and uniform, suggesting a calm, steady unfolding rather than chaotic change. Galaxies move apart, but each does so in a predictable manner over vast distances. Stars continue to shine in their galaxies, planets orbit steadily, and structures formed over billions of years persist, all within the framework defined by cosmic expansion. This steady progression provides a sense of continuity and order, even as the universe grows larger and emptier over time. It is a cosmic rhythm that can be observed, measured, and appreciated, offering a tranquil perspective on the long-term evolution of space. In reflecting on dark energy, it is also natural to consider the limits of observation. We can see only the observable universe, the region from which light has had time to reach us. Beyond that lies space whose properties are inferred, but cannot be directly measured. The influence of dark energy extends across this entirety, affecting regions beyond direct observation. By studying what is observable, scientists construct models that extend these effects into the unknown. This balance of direct measurement and inference illustrates the careful, thoughtful approach required in cosmology, where subtle forces dictate outcomes on scales far beyond everyday experience. Finally, contemplating dark energy invites a quiet sense of closure and wonder. The universe is vast, expanding, and shaped by an invisible, uniform force that governs the motion of galaxies and the large-scale structure of space. It is a force we cannot touch, yet its presence is undeniable through careful observation. Dark energy connects the early universe to its distant future, linking the light of ancient stars to the accelerating motion of galaxies. Observing it offers perspective on both the cosmos and our place within it. Though the universe may grow increasingly empty over billions of years, the understanding we gain now provides a steady, enduring connection to the grand unfolding of cosmic history. In this calm reflection, it becomes clear that dark energy is both a scientific challenge and a source of quiet awe. Its effects are subtle, its presence pervasive, and its nature largely mysterious. Yet, by studying it, humans reach beyond the familiar, understanding forces that shape the universe over immense scales of space and time. The universe continues to expand, guided by dark energy, and our knowledge grows with each observation. In this ongoing study, there is a gentle rhythm, careful observation, patient measurement, and thoughtful reflection, all revealing the hidden structure of the cosmos. Dark energy, invisible but present, guides the universe onward, and through our observations, it connects us to the vast and quiet majesty of the cosmos.